Okay, so in this video I'm going to download some Black Scholes code from kerryback.net. Kerry Back has this book. It's a really good book, and what makes it interesting is that for each of the examples provided there is some VBA code which you can find here. And hopefully if I click on that link, it'll open up this fully implemented spreadsheet with the different chapters outlined. Okay, so I'm interested in harvesting a little bit the book for its code. In particular, I would like to use the Black Scholes code here. So I'll go into Visual Basic and I'll have a look for second course in derivatives and just come down. I think it's chapter 3. And there's a couple of snippets here, but the two snippets in particular that I want is the VBA code for the Black Scholes call and put. And I would like to be able to compare that code against the code that we estimated for Leisen Reimer using this truncated lattice, truncated for the zeros. Okay, so if I come back then to go into the here in the module, I could insert a new module. Okay, insert module, so it's going to be called module 2, and if I open that module, okay, it's a blank canvas, but I'm just pasting in function for Kerry Back. So if you like, if we just grab this, for instance, copy, and then come above here and paste, and we'll just use that inverted comma. So the idea is code, VBA code from Kerry Back. VBA code for Kerry Back. Okay, so that should appear as have no effect on the implementation of our model. So I'm going to go back in. Let's just copy the first function here, Black Scholes call. Black Scholes, try that again. So I'll highlight and then just copy. And then I'll go back into the spreadsheet. And then I want to verify that this result is reasonably accurate. So I can, for Black Scholes call, that's what we had for Kerry Back. So this is Leisen Reimer, LR, and then for Kerry Back, Kerry, right? And I'll just paste the function, put an equal sign in front, and then we'll just highlight S. S is 100. K is equal to 100, R is equal to the risk-free rate, which is 7%. Sigma is equal to 30%, and then Q in this instance. Okay, so the okay, for this in this instance we're saying it was 7%. Okay, and the time period is equal to 6 months. Time period is equal to 6 months, and when we hit return, the value I get is 81564. Okay, so this is Black Scholes. Okay, maybe I should put that in here, Black Scholes call, and it's close. Can we increase accuracy? I think we can. I think if we put this up to 50, for instance, the level of accuracy goes up, so we can see it's quite accurate now. The Leisen Reimer VBA function is producing a value very, very close to Black Scholes, so they're both 8156. If I go to 100, Okay, 81564,643. What if I go to 200? Why not 500? Okay, and we can see this is quite fast, so it's 815,646, and I'll just take it up to 1000. Okay, 7, and each instance, what about 2000? Okay, we're getting closer. What about 5000? Each time we seem to be getting closer and closer to the Black Scholes value. Now 5000 is quite a big lattice, okay, but what we can note here is that the function here is executing very quickly, for the European option at least. And part of the explanation here is when we use the European option and this Leisen Reimer function, we've truncated zeros, and we're also using dynamic memory, which is a feature of the Espen-Hague style coding. So I'm going to go back to 50, but we can see we're converging as we increase the step size here. Conversion seems to be relatively visible. Okay, but I think I'll go back to 50. Okay, and we're still not too far. Okay, so Leisen Reimer and Black Scholes here relatively good, and possibly we should do the same here as well, 50. In fact, one way of, because I'm going to be using data table in a second, I'll just put equal to, so everything in the second column follows from the first column, and the only feature distinguishing the two functions here is this is for European and this is for American. Okay, and Black Scholes is true, Leisen Reimer is the approximation, but a very good approximation. Okay, so to observe, okay, one additional feature here is for Black Scholes, because B is equal to R negative Q, right? So B is like the cost of carry. Can we express, okay, B negative Q, that would suggest that Q, it would imply Q is equal to R negative B. Okay, so when I run this estimate here, instead of putting in 7 for the dividend using the parameters above, another way of getting the same values, just take R negative B and I get the same value then. So Q is equal to 7. Okay, so we can use this also to input in when we have a parameter specification that's demanding explicitly Q. I can obtain that using this B parameter by noting that Q is equal to R negative B, where B is the cost of carry. Okay, and again, if I put this up to 1000, our Leisen Reimer function gets closer and closer to Black Scholes, but I want to keep it at 50. Okay, so it's important here that I keep that at 50. Now to compare the two functions, what I will initially do is I will say, okay, let's take do a data table, and we will take both the European option value and we will take the American option value, because I would like to compare one against the other. And then I will consider different stock prices. So we'll go in steps of 10, so 10, 20, and we can pull that down, and probably because the exercise here is 100, I should go up to probably 220, something like that. And I'll just go down a notch, and then I can rerun I can take both of these columns and go to data table, right, and I re-estimate the value of both of these functions, Leisen Reimer functions, for the European American specifications. So data table, and do we have a column or a row of data? We have a column. So I highlight the second input box, and then what in the original parameter related back to the stock price, because this is supposed to represent the stock price. So I want to revalue each of both European and American options using varying stock prices. Okay, so that fills in, and I could have obtained that by a more realistic value would have been equal to, if we went to Black Scholes, right, we would have obtained the same values as well. Okay, so, and this might actually be a little bit faster as a consequence. So if I, now this is dependent on the Black Scholes value. So if I change a value here, let's say if I reduce the volatility to 20%, 0.2, everything should change. Okay, and everything has changed. So this volatility figure depends on this volatility figure here. And if I make any change in step size or so on, right, I'm going to affect the shape of the table. Next thing I might do then is, so this is the, if you like, the European option. This is the American call option. And then we might like to take a look at the intrinsic value